I'm Victoria Beal with the LTAP Center, and I'm going to be your technical support behind the scenes. I have a few housekeeping items before I turn things over to your moderator. The first thing is that questions are going to be accepted throughout the session in the question box. The moderator does plan to take questions, or excuse me, to read questions to the presenters at the end of each presentation as time allows. So please look for that question box in your GoToWebinar panel and drop me a hi or hello in there so I know that you found it and know where it is the questions need to be placed. We are not going to be taking questions through the raised hand feature because there's just too many participants on for us to be able to use that feature, but please put your questions in the question box. This session is being recorded, and if the technology cooperates, we will post a YouTube link to the video on the OTEC site once the conference completes. Also, you will be receiving a certificate for 1.5 CPDs for complete attendance at this session. If the session runs over, the certificate is not going to be modified to include any additional time. So we encourage you to stay on though if the session runs over, but please note that no additional CPD credit is going to be given. Those certificates will be sent out once the conference completes in its entirety. So with that, I thank you for your attention, and I'm going to turn things over to Mike Brokaw.
Thanks, Victoria. Good afternoon and welcome. My name is Mike Brokaw, and I'll be your moderator for this session. I work as ODOT's Bridge Inspection Engineer in Central Office in the Office of Structural Engineering. Our session today is a great session. It's about bridge rehabilitation. We have 3 excellent and unique case studies from around the state. We have 5 speakers today, so let's get right into it. Case study 1 is about the Charles Berry Bascule Bridge in Lorain, Ohio. Our 2 speakers are Luke Wysocki and Matt English. Luke works with ODOT District 3 in Ashland, Ohio, and Matt works with the Ruhlin Company in Sharon Center, Ohio. Luke, are you ready?
I am. Thanks, Mike.
Yep.
Okay. Thank you, everyone, for joining us today. As Mike said, our first presentation here is titled Raising the Span, and this is about a rehabilitation of a bascule bridge in Lorain, Ohio. So the project we're going to be talking about today is project number 2 of 18, Lorain 6, 9.67. And you can see where the pin is dropped on the aerial view here from Google Earth. This is the US 6 bridge over the Black River in downtown Lorain, Ohio. So to the north is the mouth of the river, right at the shores of Lake Erie. To the south, you have several marinas, you have a steel mill, and you also have a large Lafarge aggregate facility, and those facilities receive a number of bulk carriers to bring goods in throughout the season. The background on this structure, it was formerly known as the Erie Avenue Bridge. The structure was renamed in honor of former U.S. Marine Charles J. Berry, and Charles J. Berry was a Medal of Honor recipient in World War II. As stated, it carries 4 lanes of US 6, as well as 2 pedestrian sidewalks over the Black River in Lorain, Ohio. ADT is approximately 14,000 vehicles, and the structure was opened in 1940, so just turned 80 years old. The total structure length is 1,052 feet, and to the west there is 8 approach spans. To the east there is 1 approach span, and on either side of the river we've also got pier buildings where the operating machinery is housed, and then the double leaf movable bascule span itself is 333 feet. As far as operation of the bridge, Lorain County actually operates this bridge for the state of Ohio, and the state of Ohio reimburses the county for all of their operating and maintenance expenses on a yearly basis. So the bridge is staffed 24/7, 365 days a year. There are 4 operators that run the bridge. There's a maintenance technician, and there's also 1 supervisor, so a crew of 6. As far as operation of the bridge throughout the season, from April 1st to December 31st, the bridge operates on a regular schedule, every half hour if needed, and that's primarily for pleasure craft sailboats that are in marinas south of the bridge that cannot pass under without it being open. And then as far as commercial vessels coming into the facilities upstream, it operates on signals. So those freighters are usually scheduled a couple days in advance so the operator knows when to expect them. As far as the number of openings, in 2013, the structure was opened 523 times, but historically there have been as many as 2,500 openings per year. That was primarily back in the 40s, 50s, and 60s when there was more of a heavier industrial presence in Lorain, Ohio. So the number of openings have gone down, and that's primarily due to a decrease in manufacturing, and now it's primarily for recreational traffic on the river. So a little bit more history. The photo on the left here, you will see an existing swing bridge. So this bridge was constructed somewhere in the 1880s, and you can see the bridge was mounted on a singular pier in the center of the channel. Well, in the 1900s, as ships were getting larger, this became very prohibitive to ships passing through the channel. So the idea of the double-leaf bascule bridge came about, and you can see in the photo on the right, the bridge under construction in 1939, and the existing swing bridge in the background. So a little bit more history of the maintenance and repair of the structure. You know, any structure is going to require maintenance during its life cycle. Now, a bascule bridge comes with additional maintenance due to the complex mechanical and electrical operating systems. So from the time the bridge was opened in 1940 through the 50s and 60s, the only maintenance was primarily some painting of the structural steel. In the 1980s, late 1980s, was the first major rehab on this structure. So that included replacement of the approach span, deck, and sidewalks, as well as the electrical system, motors, and brakes. The structural steel was also abrasively blasted and painted. Then in the late 1990s, another major rehab job. There was some work on the stone masonry on the pier buildings, a new fiber optic duct cable to connect the east and west control towers under the channel, and then a new maintenance building. Then finally, in 2012, the east and west counterweights were adjusted to balance, and that takes us to our current project today. So for project 2 of 18, ODOT is the owner and was charged with contract administration. The department hired HDR for construction engineering and inspection, as well as submittal reviews. There was hundreds of submittals on this project for replacement of the mechanical and electrical operating systems, so required a great deal of technical knowledge and expertise to review those submittals. Hardesty and Hanover was the designer of record, and they were invaluable during the project as well, as there were over 200 RFIs that were submitted, reviewed, and answered as construction proceeded. And then finally, last but not least, Ruhlin Parham joint venture. They were the prime contractor for this project. So the purpose of this project was to address structural deficiencies, to provide a minimum 50-year service life for the structure and machinery, as well as a 20-year service life for the electrical and operating systems. So part of the structure work included some overlays on the approach span decks. Now, the existing approach spans are comprised of a 4 1/4-inch galvanized steel grid with a 6-inch superplasticized dense concrete fill. So what we did is a hydro demolition of 2 inches and replaced with an SDC overlay. The plan also intended a 1 1/4-inch hydro demo and SDC overlay on the sidewalks. However, that was unsuccessful. We kept punching through with the hydro demo equipment, and we ended up doing some sidewalk patching with latex modified concrete. Some of the other aspects of the structure work, approach span work, included a thin epoxy overlay. Now you can see from the photos here, this is right where the bascule spans meet the approach spans, and these are over top of the machinery rooms. So the intent here was a hydro demo and place a thin epoxy overlay over these approach span segments. As mentioned, the intent of the project was to bring up to today's standards for live loading. So some of the structure strengthening on the approach spans included the strengthening the floor beams with angles placed at the top and bottom of the webs. And this involved a very tedious process of drilling a large number of holes to bolt these angles to the floor beams. Some of the other strengthening that took place was on span 8 and the center girder, and that included adding new cover plates and splice plates to the top and bottom of this girder. And then finally, there was some structural steel strengthening out in the Bascule spans. Now, this was definitely one of the more challenging aspects of the work. You can see from the photos, all of the work is taking place from barges on the river, and we were certainly at the mercy of Mother Nature there. Being near the mouth of the river at Lake Erie, the river levels fluctuated greatly with the lake as well as wave conditions. So there were a lot of days where it was difficult, if not impossible, for this work to take place out over the river channel. Moving on, as mentioned, this is a historical structure. The control towers and pier buildings have sandstone tiles placed on the exterior. So part of the work was some architectural stone repairs, and that included some removal and replacement of stones, some patching with yawn mortar, some profiling to remove delamination, and then finally some chemical cleaning to remove an existing sealant and try and give a clean, finished look to the stone. So in the next photo here, you can see some of the architectural stone repairs in progress. The photo on the left, you can see the extensive scaffolding that was required to access the work. And the other control tower on the right, you can see some of the profiling work in progress there. Here you will find some more photos of the stone masonry work. The photo on the left here is a view of the control tower from the street level. And you can see we wanted to preserve some of the historical aspects of the structure. You've got these tiles here that have information from when the structure was designed and built in 1939. So certainly important to preserve those historical aspects. Here's another view of the control towers with the masonry profiling work completed. And this is prior to the chemical cleaning of the stones. We did chemical cleaning to remove some of the existing sealer that was placed in the late 1990s, and then also remove some of the impurities and deposits from the air that give it that kind of dirty, tarnished look. So again, these photos were taken before the chemical cleaning, but the intent between that and the profiling was to give the structure a uniform look and preserve the historical integrity of these sandstone tiles. So another unique aspect of this was actually performing some structural steel painting during the winter months. And I know Matt will get into some of the challenges with this in his presentation. But the intent here was to take advantage of the winter months where there's no shipping on the Black River, but yet maintain vehicular traffic. So in the past, when the structure was painted, the Bascule leaves would be raised, closed the vehicular traffic so that river traffic could be maintained. Well, this is very disruptive to the general public because it's a long detour to get to the other bridge that crosses the Black River. So therefore, the decision was made to do the structural steel painting during the winter months. So now I'll get into one of the other unique aspects of this project, and that was the temporary operating system. So the intent behind this temporary operating system was to maintain operation of the bridge during construction of the project. In the past, when mechanical and electrical work was done, the Bascule leaves were raised and locked into the open position so that river traffic could be maintained. Again, this was very disruptive to the general public. So therefore, this project was designed with a temporary operating system. So here's a photo of some of the temporary operating systems being lowered through the sidewalk. And again, Matt will get into more of the details here with his presentation. So finally, Last thing I want to talk about is removal of the existing machinery and installation of the new. So this photo here gives you a view of two of the existing motors and one of the existing reducers that was removed. And briefly, this slide here, the top gives you an idea of the existing machinery to be removed. So one of the intent of this project was to get everything on the same level. With the old configuration, the motors were on top and everything was transferred to shafts down below and then back up to the pinions. Kind of an inefficient design, difficult to maintain, where the new design has everything from the motors to the reducers to the pinion all on the same level. I hope you enjoyed this presentation. At this time, I'm going to turn it over to Matt English for the second portion of the Bascule Bridge presentation.
Hold on a second, Matt. You seem to be muted. Let me find it and get you unmuted. Okay, you should be good now. Try it again.
Okay, thanks, Luke. My name is Matt English. I'm an engineer and project manager for the Ruhlin company, and not a lot of time, so I thought I would just jump right into what we anticipated being the three biggest challenges for this project. And I did not get to make it to the site during the pre-bid process. So once we were awarded the project and I got to see the site, I did realize that one of the biggest challenges was not apparent from a plan review. So we'll go with the three initial challenges that we had. One was painting the main bascule span between the dates of January 1st and March 31st, right in the middle of winter on shores of Lake Erie. Second was installing and integrated the temporary operating system, or TOS, that had the same March 31st deadline. And then the alignment of the new machinery, racks, pinions, main operating system, span locks, tail locks. And some constraints to these challenges. One is the bridge had to remain open to river traffic year-round. There was a clause in there that between January 1st and March 31st, when the painting was to take place, that any vessel needing a bridge opening was to give us a 12-hour call ahead. Get back to that later. And then we're also limited that we could not close the sidewalk for more than 4 days, 2 different times, and the roadway had to remain open. Otherwise, they did give us 2 7-day closures for the whole project. So let's start with the first challenge, and that was the paint. Now, nobody on earth loves the ODOT 514's painting spec more than I do. And despite the love of that spec and the perfect harmony that always exists between the contractor and the department when it comes to paint, I had a great deal of concern about trying to do this in the middle of winter. I actually questioned our sanity for taking on this risk. That, coupled with the fact that we're leaving our fate in the hands of a painting subcontractor, only added to that concern. And in typical fashion with time-sensitive and critical activities, it was pretty spectacular how much work was not progressing the first few weeks of this project. So here are a couple pictures of both inside and outside the containment. And in defense of the painters and the slow start, the containment had to be moved because had to be done in stages because the road had to remain open. And because of that clause that we thought we might have to open the bridge with 12-hour notice, we initially tried to do the containment so it would be operable with a bridge opening. But that was just not possible. And plus, there's a whole balance issues with trying to do containment. So we were able to work with the Coast Guard and the local businesses, and most of the closure period, we were assured that there would be no bridge openings. So was the painting a challenge? It absolutely was. Did it go as it planned? Absolutely not, but I will give it to the painters. We were able to do this with some complex sequencing and a lot of pushing, but it did get done. The next apparent challenge was the installation of the temporary operating system. And if this wasn't a challenge enough, we had to get the TOS installed, integrated, and operable in the same deadline as the painting. So when the painting was off to a slow start, we knew on the back end there'd be less time to get the TOS installed. That was Wasn't a lot of fun. Luckily, us engineers don't worry about that stuff too much. So there were a few challenges with the TOS itself. In this picture on the left, you can see our ironworkers checking the fit between the trunnion and the hub. That particular clearance was 0.02 of an inch. That's 0.002. And some of the risks we take as a contractor for a project like this is the specs are written as if we were doing this room in like a climate controlled clean room. So it's always a fun part of that job is trying to maintain the tolerances. And then this is the middle picture. It shows the trunnion in place in the actual Bascule truss. Part of the evolution of this design is we actually had to have more reinforcement to the truss. And with more time, the TOS itself would be just its own standalone topic for one of these presentations. And then here's a picture of the finished TOS cylinder assembly. You can see the trunnion way up here at the top and roughly 45 feet from the trunnion to the blind end of the cylinder. Not so much a challenge, just some interesting facts that this hydraulic cylinder had 16 feet of stroke, and it actually raised the bridge by retracting, which was pretty counterintuitive to how you think that would work. So was the TOS a challenge? Definitely was, but we got a good team here at Ruhlin, and even in the condensed schedule, we were able to pull it off in time. And the last of the obvious challenges was the machinery alignment. At the time we were bidding this job, I was actually on another Bascule bridge, and we were having a monumental struggle with the open gear alignment. So anytime you're aligning new components to old components, there's always a challenge, always a risk. In the bottom left picture here, you can see we were doing some checks of the rack alignment with some dial indicators, checking the pitch line and rack runout. And on the right, we have a picture of checking the mesh of the pinion and rack gears with some bluing. And there's always like a running joke when you struggle with the alignment on these machinery components. Well, it's a joke. I don't know if the owner always finds it funny. Like, don't worry about getting exact alignment. It'll eventually wear itself in. And for the existing span locks, they were definitely well worn in. These were a challenge in the fact that we were connecting two separate structures with a new piece of machinery. And over the course of the last 40 years or whenever these been changed, there was quite a lot of iterations. So this is just another example of the risk the contractor takes. You really can't tell just how bad things are going to be until you rip the old system out. We had a lot of iterations of changing rear and front live loads. And the old system actually pulled the leaf down into contact, which we were not allowed to do with the new system. And there's just a few more pictures of some of the machinery alignment. The left is a picture of the tail lock. In the middle, it's just an interesting picture of one of the primary reducers. And that has nothing to do with alignment, but that machinery room cover that you see on the right was quite the challenge. So all these challenges were fairly obvious going in, and they were a challenge. The alignment of this machinery actually went better. The design was very good. It used a primary differential reducer, which was much more alignment friendly when compared to some of the other designs we've used. And we also employed Bob Polsett from Stafford Banlieue Engineering, which made this process go very well. So 3 obvious challenges, all were a struggle to some degree, but went well. But the less obvious challenge that you cannot identify from just looking in the plans was we had no idea how we were going to get each of these components into position. What you see on the left is a rack. In the center is the secondary reducer. And on the right is the main pinion. Now, none of these components are that big to say setting a bridge girder. The racks were 22 feet long and 12,000 pounds. The secondary reducers were huge by any standard. They were 6 feet tall and weighed almost 20 tons. And we routinely handle things this large or larger, but how to get these into the point of installation became quite the planning session. We determined there were 2 possible routes to get these components to where they needed to go. First one was through the pier house and across the counterweight pit. So they had to go through the double doors in the picture on the left. Then once through the double doors, drop 25 feet down to the counterweight pit floor. And then across the counterweight pit floor to the trunnion tower, up another 25 feet through the laterals of the trunnion tower and then into the machinery room. All this had to be done with no crane and inside of a room that's periodically completely filled with 2,000 tons of steel and concrete counterweight. So we quickly deemed this path impossible. So path number 2, we thought maybe we could do it from the channel side. So we had a picture with the bridge down, and we thought maybe with the bridge opening, we could sneak into where the machinery room is exposed in the middle picture. But with the lack of road closures and trying to do this with just traffic stops, we figured we'd have 15, 20 minutes, half-hour tops to try and bring in a crane, and still we had to struggle to get underneath the bridge. So we abandoned this idea pretty quickly and pretty much determined that the impossible path was the way to go. So this turned into quite the planning session. Many ideas for how to get the machinery through the pier house. Thought of an upper track system using Hillman rollers to mighty mini jacks on a lower track system. Thought of a ramp down to the counterweight pit floor, highline systems, chain hoist, air tuggers, conveyor belt system. Even came up with a temporary false work rail system, kind of like a mini roller coaster inside the pit. Rolling gantry on the pit floor, overhead crane. All those had problems, and once you got it to the floor, you still had to move it. So we thought about maybe industrial forklifts or air dollies. And then we had an idea, maybe we can just sub this work out. So we called in a specialist in industrial equipment moving, brought them out to the site. They looked at it for about 20 minutes and told us they had no idea how they would do it. So that was over. And then we thought maybe we can get some specialty equipment, particularly equipment named after animals. Checked the spider crane and something called a platypus, which was some compact tracked container mover. Our superintendent saw somewhere. So we tried all of these things, a combination of all of the above. But no matter what we tried, none of these things could solve all the problems we were looking at. So this went on for a while, and we were stymied for a while. We even got bonus time to be stymied, as the project had a fairly significant delay trying to find a domestic manufacturer for the brakes. But we did finally, in fact, have a breakthrough and the ingenious and highly technical solution. Let's cut a big hole in the road we just repaired. And I'm not totally sure who came up with this idea, but since I'm the only one speaking today, I'm going to take full credit. And even this idea was not without its problems, as the machinery room, as Luke mentioned, is not directly under either of the spans. So it was right on the joint from the transition from the lift span to the fixed span. So this required quite a lot of removal of the steel we just repaired and painted. But we were pretty happy that we finally had a working solution. And here is a few pictures of the rack placement from the hole in the roadway. And just getting the racks into the counterweight pit wasn't actually enough, because there was a lot of work afterwards. Pretty much just left it up to our iron workers to do a lot of rigging and a lot of different moves with different rigging setups. So I'll give them most of the credit. Once we got it to the floor, at least for the racks, they were able to get the stuff into position in very short windows between bridge openings. And the tightest fit that we had was for the secondary reducers. We had about 1/16 of an inch clearance to get these into the hole. And while I make fun of this solution is not glamorous, it did create quite a bit of engineering, because even once they were into the machinery room, they were all offset from the center line. So moving a 20-ton reducer with no overhead crane is much easier said and done. So there was a pretty complex system in the machinery room with Hillman rollers and a lot of complex rigging. And then lastly, this was the main operating machinery going into the machinery room. So I know that is kind of quick, and I don't know how much time we have left, but if you have any questions or I went too fast, please feel free to email me at menglish@ruhlin.com. And with that, I will pass this over to Jay.
Thanks, Matt. There's a lot to unpack in there. We did get a few questions, and those that asked will get individual responses from Luke and Matt. So thanks for jamming that into quite a small amount of time. There's a lot in there again. So thanks again for putting that together.
All right, very welcome. Let me get this to Jay here.
Our second case study, while Matt's bringing that up, our second case study is about a bridge in District 11, Belmont County, State Route 7. The topic will answer the question, how to strengthen deteriorated T-type pier caps using external post-tension bars. Our speaker is Jay Lee from Burgess and Niple here in Columbus, Ohio. Jay, you set to go? Oh, almost. You got to unmute yourself.
Oh, thank you.
There we go. Yeah, you're welcome.
I appreciate for your wonderful introduction. Hi, my name is Jay Lee, and I'm currently working for the Burgess and Niple as a bridge engineer. Thank you for joining OTEC virtual conference. Today's my topic is bridge pier cap strengthening using external pre-stressed tendon bars. A couple years ago, we worked on this project, and this was a very unique pier cap repair, and it has very limited use in Ohio. So we decided to give a presentation in OTEC and shared our experience today. Also, we hope this presentation might be helpful to you if a similar situation or project that happen in the future. Before we start the presentation, we would like to tell some story about State Route 7 first. This red line is the State Route 7. State Route 7 was called Inter-County Highway 7 until 1921, and then it changed to State Highway 7. Basically, it runs from north and south of east of Ohio along the Ohio River. Total length is about 336 miles, which is the longest state route in Ohio. I marked up the blue circle on the map, and then that's the city of the Bridgeport in Ohio. Today's presentation is about the bridge located in Belmont County over this State Route 7. This is the Belmont 7 bridge was going to study today. The original bridge was built in 1968 and the rehab in 1998. Mostly replaced the parapets, medium barriers, and resurfacing on the deck. The bridge has 21 span, and the total length is over 1,600 feet. The bridge has 5 units, and each unit has cantilever hinges at the end of each unit. As you can see the picture, as it yellow, these are the typical 36-inch wide flange rolled beam at the unit 1, 2, 4, and 5. And middle span with the green color is the 6-inch height, the web steel plate girder over the Wheeling Creek. Northbound and southbound are separately, but these are the two twin structures. The deck width about 35 feet each direction, and then design loading was a CF2000. The Belmont 7 Bridge project has been carried out in 2 stages. The first, we have done temporary pier cap strengthening design until they are replaced to new pier cap or replace the bridge. The second, we studied the bridge rehab and replacement. The ODOT asked us to study 2 options for the bridge. One option was replace the bridge with a 3-shoulder bridge with the MSE island. This could be possible because the proposed bridge does not need to as the same as existing bridge span lengths. The other option was rehab the bridge by replacing the superstructure and the pier cap. Today, we'll talk about the first topic, the pier cap strengthening design. After more than 50 years bridge service, many of the pier cap were found as serious cracks and deterioration. Some pier cap have a very big area of delamination and spalling, and abutment have a tilting issue. Also, severe deterioration found at the top of the pier bearing seat. So, ODOT decided the pier cap need to be repaired. This is the typical vertical cracks happen in the most piers. This is the Pier 8 eastbound, and looking at the rear side of the pier, as you can see, the bad concrete area already marked up on the pier cap from previous inspection. So we could see easily where was the limits of concrete delamination. This is the Pier 11 westbound, and looking at the fore side of the pier. The same as other piers, there's lots of vertical cracks on the pier cap. And this is the Pier 16 eastbound. These vertical cracks were found to be growing over the year. So this vertical crack was the main reason we need to replace the pier cap. This picture shows that some place has a chunk of concrete was missing and a big area of spalling. So based on the pier cap condition, ODOT decided they did not want to salvage this pier cap. The pier cap condition was getting worse over the year, and ODOT wanted the short-term fix to make sure the bridge was safe until the rehab or replacement of this bridge, which could be built several years later. So they asked us to study several options for doing the short-term pier cap repairs, and then we prepared the construction plan as soon as possible. ODOT selected 6 piers for expedited repair, and they were Pier 8, 11, and 16. There was also a transverse crack along the face of the pier cap, so we could not give a pre-stress force in this condition. We will talk about in more detail later how we handle this problem. We considered supplementary support members will taking care of most of the dead load and the live load. So we tried to minimize to use the existing pier cap capacity if possible. We proposed 3 different types of temporary support option: steel frame type support, steel beam type support, and external post-tensioning support. This is the first option we propose for temporary support. It's the frame shape and support the girder adjacent to the existing pier. Put the 2 14-inch H-pod column on the top of the pier footing, and then place the wide flange steel beam to support the existing fascia girder. One of the benefits of this method was it does not need to repair existing pier. However, this method was changed to support the location from original design, so it can cause a tension stress on the top of the deck slab. Another option was to big size of the steel beam with the support brackets. We can attach the bracket on the pier column to support this beam. It uses less members than other method, so it is a relatively faster construction, but because of the heavy support beam, it could add a serious extra dead load on the existing pier. And it is not easy to drill the hole without cutting the pier column reinforcement, so that might be a problem. This is not the exactly same photo what I'm talking about right now, but it is a similar idea. How does it work? This is the picture about the formwork for the concrete pier cap. Third option was external post-tensioning, and ODOT selected this method. They basically installed the anchor plate on each side of the pier cap and post-tensioning force on existing pier cap using 6 high-strength post-tension bars, so it can increase the existing pier cap capacity. This method was the least dead load on existing pier when it compared with the other three options. Based on the engineering cost estimate for this method, total construction cost was about $300,000 and award amount was $228,000. Existing bridge analysis. To calculate the initial stress force, we had to know how much dead load and light load force were working on the existing structure. So we modeled superstructure using Midas and calculated all the reaction force at each pier. Based on this reaction, I just a quick check for the bearing capacity, and it seems over 90% of a performance ratio, which was okay. Also, we checked the original design capacity for the pier 8, 11, and 16. Pier cap still was adequate, but the shear strap was not enough strength for HS20 live load. We already knew that many Asian countries like South Korea, Japan, and China, they have been used this type of construction for a long time. So we thought it would be very easy to find a similar case in here because this situation could easily happen here, and this method was not that difficult or special thing. So before we start to work on this project, we look up the ODOT archive or like a historical project database if we can find a similar project like this. But unfortunately, we couldn't find it. Generally, in Asian country, as design light load became heavier over the year, the bridge owner, they wanted to upgrade existing structure for higher performance. So in such a case, they have been using this type of method for pier cap retrofit. This screen is the rendering image to explain how external post-tension bar are working on the pier cap. Basically install the anchor bracket or anchor plate at each end of the pier cap and then post-tensioning with a high strength bar or strands. One thing I noticed that is they use the saddle bracket at the top of the pier cap, so it could push more pre-stress force on the existing pier cap. And also they use this method sometimes for temporary condition, but sometimes they use for permanent construction as well. These pictures are showing how they proposed the idea to bridge owner or their client to retrofit both of concrete beam and the pier caps. If you see the left picture in the showing concrete beam, they added to external anchor bracket at the bottom of the beam, and then post-tensioning using typical standard pre-stress strands at the bottom. So they upgrade the concrete beam as well as the pier cap at the same time. So I had some internet research and I found some similar project in US. This is the George Wade Memorial Bridge located in I-81 over the Susquehanna River in Harrisburg, Pennsylvania. A bridge was built in 1969 and the total bridge length is 5,200 feet. Early 2000, PennDOT figured it out, pier cap reinforcement was not enough to handle the current traffic load of 32,000 vehicles per day. They also found some vertical cracks on the pier cap, as the same as Belmont 7 Bridge. So PennDOT decided to repair this pier cap structure. The retrofit work has been done in 2010 by Dividex System International. They used 6 post-tension bar with a diameter of 46 millimeters. They retrofit total 68 piers, which were each 34 piers for northbound and southbound. In the left 4 pictures, these are another example how to attach the end plate if the pier cap has a round shaped corner. I don't think it is not effective as much as a typical, like a flat shape of ankle plate, but if we have to do something for repair, I think it really works. The right picture on the screen is the example how to strengthen the pier column using post-tensioning strands. So from this research, I have learned that many other countries are developing their own retrofit with a various method or ingenious idea. Okay, now let's talk about the design procedure. We calculated all the dead load and the live load reaction from existing bridge and decided the size and numbers of the post-tension bars. We also created the existing pier cap model using Midas and then applied all the load, and then we checked the pier cap concrete stress. Once it passed, then we checked the stress for the post-tension bar and then ankle plate assembly. This is the screenshot for the pier cap Midas model. We did not show the superstructure Midas model in this slide, but definitely we did the superstructure member analysis first. And then we applied all the reaction forces on this pier cap model. After calculating the reaction and the post-tension force from the Midas, we imported all the member forces into the spreadsheet. We create the macro to run with the code checking spreadsheet and then calculate the final concrete stresses. In this spreadsheet, basically it checked the existing concrete factored moment and the concrete service stress, as well as the post-tension bars tension stress. For concrete stress checking, we have to check all the 3 different cases of concrete stresses per AASHTO code. Once we finish the pier cap concrete stress, then we have to check for the ankle plate assembly for next. We took a middle section of ankle plate, so it was a shape like a cantilever with a T-shaped section, and then applied the half of the prestressed force on it. This was so simple question, so we just calculate by hand. Finally, we calculated all the ankle plate stress at the top and bottom, and then verified that everything was under allowable stress. This is the pier cap concrete, the patching diagram we provide in the construction plan. And the bottom picture is the actual pier cap photos before we start the concrete patching work. And this is the Pier 11. In order to draw this diagram, we have investigated entire pier cap to verify if there is additional delaminate areas. Some of them were good, like no marked anything, but actually when we tapped the hammer with the pier cap area, we found some additional delamination, so we have to include this in the concrete patching diagram. This is the Pier 16. In the construction plan, we have to provide concrete patching directions. Most case, saw cut shall be provided around the perimeter of the removal limits. Especially end of the pier cap repair, we removed all the bad concrete to provide the undercut shoulders as shown as pictures. Another thing we found at the bridge site was the end of the pier cap concrete surface were not flat and smooth. Mostly the gap was between 1/16 inch to the 1/4 inch. So we provided some detail in the construction plan. If the gap was greater than 1/16 inch, then the concrete shall be grounded to make a smooth and a nice flat surface. Even though we grounded the beer cap concrete surface to make it flat and smooth, we used the fabric pad to better contact between the end plate and concrete surface. The pad thickness was 1/4 inch, and the material was the same as a typical preformed bearing pad per CMS. About the post-tensioning bars, we have used 3 high-strength post-tension bar at each side. Grade was 150 KSI steel and 1 inch diameter with all threaded bars. Total final jacking force was 60 kips. The first, we used the 15 kips for initial jacking force for each bar, and then finished up the jacking force by 60 kips. So we have 2 incremental jacking work. We installed the bar clamp to prevent the sagging due to the post-tension bar self-weight or possible vibration. This was a typical clamp used to secure the pipe to the wall. The rubber bushing was a little bigger than the post-tension bar, and the clamp was made by stainless steel. We used 2 of these along each post-tension bar. Also, we used a 3/8 inch diameter anchor bolt to secure this clamp. This is the anchor plate assembly. Mainly, there was a 2-inch thick steel end plate attached with the 4 horizontal stiffeners and a 1¼ inch thick individual anchor plate at the end of each post-tension bars. All steels were 50 KSI and the galvanizing steel. Another design challenge was we have only 1 foot gap between the end of the beer cap. So we have to design the anchor plate assembly should be less than 6 inch for each side. Ended up, we designed the anchor plate to make it work, and it has 1/2 inch clearance between the stiffeners. So to be honest, we were worried about it. The contractor could fabricate this assembly exactly by the plan and install this precisely because they were almost touch each other. When we revisit the bridge site after construction, contractor did really good job, and we were really very happy with that. So this is the picture. All the installation has been completed for the Pier 8. And this is the Pier 11. And this is Pier 16. As you see the picture, it was a very simple design and a very effective repair method. Also, it was relatively easy construction. So I guess this was the perfect solution for the beer cap repair with this problem. In this project, we have used this method as temporary repair for the beer cap, but I think definitely we can use this method as a permanent method as well. One more thing we would like to share with you is some reference report. This is the FHWA technical report, and then title is Report on Technique for the Bridge Strengthening. I think it published in early 2019, so we could not see this report during our project, unfortunately. But basically, it talks about how to calculate the capacity and the load rating factor for existing and after strengthening beer cap. So this report might be helpful for the bridge engineer who use this beer cap strengthening method or load rating analysis for this type of the beer cap. So this is all about I prepared for today. I know it is a very short time, so definitely I did not show the other things, but if you have any question, you can send me the email. That is the best solution. So I'm going to forward to next slide to the Blake.
Jay, we do have a couple questions. We might have a minute or two
Okay, sure.
while we've got you on. First question is, does the external post-tensioning keep cracks from propagating?
Actually, after installation, we did not looking at it, but this one is the temporary method. So I don't think it was not happening, but I'm not 100% sure.
Okay. Next question, the pier cap overhang is overstressed and shear for HS20 live load. How does pier external post-tensioning increase shear capacity?
No, I don't think so, but we study a lot of what is the cause for the disc crack, but we don't know. It could be like a heavy live load or over traffic load, or maybe it happened the cause for the transverse temporary expansion. We don't know. But ODOT already decided that they're not going to be salvaged the pier cap, so we did not actually focus about that.
Okay.
That's a good question. Yes.
I'm gonna keep hitting you, Jay. Can you explain why piers 8, 11, and 16 were the only piers needing repair? What were the conditions, the other ones?
Right, that's a good question too. Definitely, there is the most, all of the pier cap has a crack, but was not really kind of critical. So these are 3 pier is the most critical conditions. So ODOT, they want to repair as soon as possible.
And last question for now, we got some good ones here, but did you consider using carbon fiber?
I don't know about the construction cost, but this I don't know, that will be more expensive, but we did not consider that one. But I think the construction cost-wise, this is very kind of competitive. I think it will be much better cost-effective.
Okay. Well, Jay, thanks for your time. Good presentation. Stirred up some good questions. Those that do have questions, we will have Jay respond individually in the box, and you also have Jay's email to directly contact him. Let's move into our third case study.
Thank you.
About yeah, thanks, Jay. It's about a suspension bridge we share with our neighbors to the south over the Ohio River. You'll hear what was found and what was done. Our speakers are Blake Jones from Kentucky Transportation Cabinet and Jason Stith from Michael Baker International. Blake, you ready to go?
Yes, sir. Thanks, Mike.
Yep.
As Mike mentioned, I'm Blake Jones, and I've got the privilege of presenting this presentation with Jason Stith on the Simon-Kenton Bridge Temporary Suspender Retrofit Project. I'm going to go over a little general presentation overview. I'm going to go over some general bridge views, some photos that we've got from our inspections, some bridge terminology, some basic bridge terminology, summary of findings from our last 2019 fracture critical inspection. And at that point, I'll hand it over to Jason Stith to go into the details concerning the suspender, the emergency suspender retrofit design. And then we'll obviously conclude with some conclusions. There's a couple mug shots of me. I'm the KYTC on the south side of most people on this conference in Kentucky, the District 9 bridge engineer for Kentucky. For those of you who do not know where the Simon-Kenton Bridge is, it actually crosses the Ohio River, and it connects the city of Maysville to Aberdeen, Ohio. This is roughly located 75 miles upstream, which is located southeast of Cincinnati. A little bridge history. The Simon-Kenton Bridge is a suspension bridge built in the 1930s. It's got ties of its designer and then the fabricator's shop drawing, or the persons in charge of the shop drawings actually have ties to the Golden Gate Bridge and the Brooklyn Bridge. So a historic significant structure. The navigational span is 1,060 feet. The overall length of the bridge is just under 2,000 feet. The towers extend vertically approximately 125 feet above the bridge deck elevation. It's a narrow 2-lane bridge with a very narrow sidewalk. So narrow, in fact, you do not walk side by side on this structure for fear of getting taken out by a truck mirror. The next slide I've got, the next slide that we have here is a typical elevation view. It's upstream of the structure, of the upstream side of the structure. On the left, you can see Maysville, Kentucky, and on the right, you'll see Aberdeen. It is a fracture critical bridge, and what we do is we share this bridge with Ohio, but Kentucky is responsible for the maintenance, the inspections, and letting out contracts for the structure. And this structure is so large, we actually do not inspect it with our in-house forces. We actually consult out, and that's where Michael Baker and Jason Stith come in to the picture. So it is actually consulted out every 2 years for fracture critical inspections. The next photo we have here is looking at the end view of the bridge. On the left-hand side is the downstream side with the sidewalk, and on the right-hand side is the upstream side. And as you can see, the lanes are very narrow. The bridge is roughly, I think our driving widths are roughly 20-foot curb to curb. The next slide that I have, or we have for you guys, is actually a little, it's got some terminology labeled on the structure. You got the main cables that drape over top the towers, and then the suspension cables or secondary cables that are in question that we found the critical finds at are actually the vertical cables that drape over top of the main cables and connect to the stiffening truss onto gusset plates on the outboard and inboard faces of the stiffening truss. One important thing from this photo, it's hard to tell, but it's important to note that the suspender cables, it's actually one continuous loop. At the top of the cable, it goes over the top of a cable band, sorry. So it is not two individual cables, it's one cable. If you cut it in one location, you essentially lose the entire suspender. The suspenders are considered fracture critical. Loss of one of the suspenders, it's deemed that the stiffening truss is not capable of carrying the load between suspenders. So loss of one of those could result in partial failure or complete failure of the structure. The next photo, or the next slide we have, is a close-up of a gusset plate connection where the suspender actually connects to the stiffening truss, as we talked about in the previous slide. The cable comes down in between two, I guess, angle housings, if you want to call them, and connects into a socket. The socket is where the cable comes down and it splays out into what's that bell-shaped device at the bottom of the connection. And it was actually formed through a casting process using molten zinc. And so where we found the critical finding was found by Michael Baker during the fracture critical inspection is right above that socket casing in between the angle housing of that cable, right down below. And anybody that's done bridge inspection can tell you that this is just this little area was just made for collecting debris, holding moisture, and accelerating corrosion. So that is where our critical find in 2019 came from. We'll go on to our next slide. There's a little bit of a delay, but our cable or the suspender cables essentially consist of individual wires spun together to create a strand. In our case, for our suspenders, we have one core strand in the middle with 5 separate strands spun around it. So this just gives you a little bit of a visual of what we've got out in the field. So, you know, what happened in a little bit of history about behind the bridges. Up until 2017, the suspenders really didn't have any major notable defects. I'll say that. They had minor defects. In fact, the suspenders were considered in satisfactory condition with a note that basically said up until the 2017 inspection, at isolated locations, there is pack rust between the housing angles and suspender cables at the stiffening truss connections rather, sorry. The suspender cables also exhibit surface rough and corrosion at these locations. So at worst, for any of the bridge inspectors in the room, this would result in a condition state 2 rating if you do element level inspection. I know ODOT is getting ready to move to that. I think Mike's extremely excited about that. Mike Brokaw is. But just a little summary or a little exhibit for those of those rooms that do not do element level inspection. Condition state 1 is good. And this is specifically for the element of suspender or secondary steel cables, which would be our suspender cables. Like I said, condition state 1 is good. Condition state 2 is freckling, rust, corrosion of the steel is initiated, but there's no section loss. Condition state 3 is section loss is evident or pack rust is present, but does not warrant structural review. And then at that point, when you move into condition state 4, you're moving into a situation that warrants structural review, basically stating that that element can no longer carry the loads that it was intended on, and a engineering analysis needs to be performed to determine the weight carrying capacity of the structure. The next slide we have is going to be a picture of that connection that is in good condition. Okay. And as you can see here, there's just you know, the paint's in decent condition. It's starting to kind of chalk a little bit, but for the most part, we've got no surface rust or no major surface rust and no section loss. And that's how we want that connection to look. Unfortunately, in 2019, while I was on vacation, of course, it always happens when the bridge engineer's on vacation, our consultant found a critical find at multiple locations. The location we're looking at here is upstream M41. And as you can see, there's some very advanced corrosion, section loss. If you squint your eyes real closely, you can actually see a couple of the strands are actually broken in this photo. And we'll actually zoom in on that in this next slide, if it'll open. And here you can see those couple of broken wires. I said strand, but broken wire. And it's really hard to actually estimate the amount of section loss here, because as an inspector, you're imagining what you can't see encased behind this cable between the angle iron could be much more severe loss. So you're actually assuming it's worse what you can't see. So this is a pretty notable find. The next slide we're going to look at is a couple panel points down or away from this location. It's also on the upstream side of the truss at M43. I will say the 4 worst locations, or 4 of the really critical locations, actually all were right in a row, which also gave us a great deal of concern. But what you'll see in this next photo, where the arrows are pointing to, it's an isolated critical find, but it was present at this location. You can actually see the cable is bulging. And what this indicates to us is that the center core, if you can remember back a couple of slides earlier, where we had a center strand, that center strand could be broken, coming undone, or coming untwined. Or advanced section loss on the interior of that core strand, but really nothing good is apparent from this slide. We really don't know the severity of it. We just know it is definitely critical. And this location was extended about 2 feet above the stiffening truss, above that anchor house and or not anchor house, I should say, those angles and the gusset plate. The next photo we're going to look at is at that lower connection point at upstream M43, and you can see the section loss is very similar to M41, if not worse. And this just kind of gives you an idea of what we're coding a condition state for. So, like any good engineers, we went back to the old inspection report immediately to try to see what happened. You know, was there advanced acceleration? Did we miss something in the previous inspection? And as you can see from this 2017 photo at upstream M39, there is some surface corrosion and some section loss, but I will say there's clear evidence that it has advanced greatly in the last in between 2 years between the 2 inspections. What that led us to conclude, basically this next slide shows what we concluded after the fracture critical inspection was complete, is we have 136 suspenders. Up until 2019, all the suspenders were rated in condition state 1. We might have had a little bit of oversight even on my part on that we should have had some in condition state 2, but it's a pretty drastic change to go from 136 in condition state 1 in 2017 to in 2019 to 16 in condition state 4, 23 in condition state 3, 11 in condition state 2, and then the remaining 86 in condition state 1. We put this bridge on 1-month special inspections following this, and I think by the time we actually let the emergency contract, we upped it to 19 condition state 4, 19 repair locations, and we ended up actually closing the bridge in November of 2019, following, I guess, a few months after this July inspection for a couple of reasons. One, we could not keep the truck traffic off the bridge and keep it open at the 3-ton posted weight limit. And then two, we also thought we had visual evidence that bulge at upstream M43 had actually gotten worse within a couple months. So we immediately closed the bridge in November. With that, I'm going to pass the presentation over to Jason, and I think Jason's going to start talking at this point.
Yeah, thank you very much, Blake. I appreciate the introduction and starting us through this. So what we ended up doing on this project, as Blake said, after we went through and found the critical finds, where we had strands that had multiple strands, not just multiple wires broken, but some of those had 100% section loss of the truss itself for the loss of suspension. Blake mentioned that was something that we had to do as part of our task, and what came of that was that the compression member of the truss was insufficient to handle the load from the loss of one of these suspension cables. So we had no load path redundancy, which added urgency to our situation. Next, we had to develop the emergency detail. I know that probably you don't have a lot of cable structures on your inventory, and those that do, I think it's important that there's not much information in AASHTO for these kind of things. So one of the things I want to get out of this presentation is to provide some background and ideas of how you can handle these situations. And so basically we went through and said, can we make a rope clamp that could fully support the suspenders and allow for the detensioning that would be used during the replacement, or in this case as a backup belts and suspenders of the existing. But because of that, this problem is not something you'll find in AASHTO. So I want to spend just a few minutes here describing how we designed this, and if you needed to do something similar, how you would be able to go about this. There is some information in Euro codes we were able to find on the design requirements for this, and I think it's very helpful. It allowed us to feel confident in the stuff we were doing and how we came about our answers. So essentially, we're going to take that clamp. You're going to take some plates, and we're going to cut a groove down the center of it. That groove should be slightly larger than the cable, and you can see those requirements that the Euro code uses. In addition, you want to have most of the cable encased in that groove and resisting the friction. You don't want to have it kind of pinching just on one side. So to have that total angle, or that alpha that you see there in the picture, should be greater than 250 degrees. Again, requirements that help you in the design process to ensure that we're detailing this correctly. The next part of this requirement was a pressure. You don't want to squeeze too tightly on these cables. That is part of the problem we have with the reduction in fatigue capacity. And so they have a requirement for a little 7 1/4 KSI of pressure, clamping pressure. And so you see use the 0.16 for your friction coefficient. We also found some research that New York DOT had done for a similar system and found that friction coefficient to be 0.27. We went in with a more conservative number, the lower number here for our stuff, but there is limited but some information out about that. Finally, the slipping force can be calculated so we understand what our clamping. So a slipping force is how much load is in the cable itself. And this, with the friction coefficient, defines the clamping force. The clamping force for our situation is taken by the bolts, the pre-stressing of the bolts you have here. So this slide here kind of gives you some general idea of what we had. Again, your situation when you have something like this will be different, but for illustrative purposes, I think it's useful to kind of think through. The suspenders were 1 3/4 inch wire rope. Therefore, our groove that we cut in the clamping thing was just slightly larger at 1 7/8. Our design load for each of these clamps was 125 kips. And that is the friction that we needed to resolve in the clamping, the resistance and the slip force. And again, that clamping force is done by that bolt pre-tensioning. So we ended up using 12 1-inch bolts to get the appropriate amount of clamping force. From there, we could design the plates to ensure that they don't yield. There's also kind of a serviceability check there, right? So we have a gap between the two plates, and we want the clamping force to be going through the wire itself and not with that, if that gap were to close, the transferring between plate to plate. And so for our situation, we had kind of what I call a serviceability check to ensure that that gap or the design displacement of those two plates is not too great. One other point on this slide before I move on, it should be noted again, the bolt pre-tensioning provides your clamping force. So it was very critical to us when we got stuff that any fabricator should be able to pull off the shelf and immediately be able to put into this thing. And also by doing that, we reduce the weight of any single component, making it easier to fabricate and easier for a contractor. Design, and I won't go into further. I did want to emphasize again, there is fatigue concern with this. So as you have that clamping force gripping onto the wire or the rope in this case, you're going to get additional pinching of the wires, and it's going to cause additional wire fretting. From the tests that were done, and I left a link in here to where we had seen some of these tests, they were reporting fatigue losses or fatigue reductions of 60 to 80%. So while these cables were originally designed for infinite fatigue life, if you run through those analysis, even with that, you're going to have a significant stress concentration. So this is not a long-term solution. We put these in here to act as a belts and suspenders, but not to be a permanent fix to this problem. So while the detail you saw earlier works well for the long suspender cables, the suspension cable, the main suspension cable, actually sags fairly close to that stiffening truss, nearer to midspan. Now this main cable is actually 61 51 strand wires running through here with this outer protective wrap. This was all checked out years ago. We also opened up a few of the hatches to assess the cable as part of this, and they turned out well. The next thing that Blake showed earlier and talked a little bit about on the next slide here is the cable bands. And so these loop over top. There's 131 of these cast steel cable bands, one for each of those suspension cables. There's various angles and different degrees. I think it's interesting to note that these are detailed on 1/4 of one sheet of the original plan set. To have that many different castings all come out of one 1/4 of one plan sheet is remarkable. Those old guys knew what they were doing. For the shorter suspension cables where you couldn't get all that apparatus in before, we went with this system, and essentially we put a U-bolt over top of the main cable. We put a bent plate with a thin rubber sheet to help try to distribute the load, make sure we're not pinching any of those wires that are protecting our main cable up there. And then we have another bearing block, and again with all threads coming down to the main cable. So this was the detail. KYTC is currently looking to program the long-term bridge replacement portions of this thing, and I think that is coming down the line here shortly, and will be part of a future repair to this bridge to ensure it stays within the inventory and its historic nature is preserved for years to come. So with that, I appreciate your time, and thank you very much. Blake and I are willing to take any sort of questions you may have at this time.
Yeah, thanks, Jason. Thanks, Blake.
They may become more permanent than temporary at this time. We do not have any funding programmed at this time to do the full suspender replacement. The full suspender replacement that Jason's alluded to has about a $10 million price tag. And we also need to program about $10 million in to paint the bridge and do some joint repair work on the structure. So at this time, we do not have that in our highway plan. The way Kentucky does it, we have what's called a 6-year highway plan. And we nor ODOT have programmed that funding in at this time. But we're hopeful in the next 2 to 3 years.
Did you tell us, or how long was the bridge actually closed? Was there a time?
It was
weeks or months.
It was months. It went from about November of 2019 till about April, May-ish of 2020.
Okay. And back to the main cables. Could you describe the hatches in the main cable that were opened in 2019? Installed in 1979 and opened in 2019?
Yeah, if you go back up a few slides to, I have a picture of one of the hatches there on slide 28. Yeah, right there.
Oh, yeah, here we go. Got it.
Yeah, so right there, what they did back in the late 70s, they actually, so the cable has parallel wires, those 51 wire strands running through it. And visible corrosion near the sags of those of the main cables. So they position them at the ends in the center of the bridge approximately, but a little ways kind of in between the actual bands where the suspenders were attached to make sure that they weren't interfering with it.
Two questions to go. Was there any discussion about the possible use of cathodic protection to prevent further corrosion?
We ended up doing a contract mod,
Doesn't sound like it.
Thermarust. But no, not yet at this point. So.
Yeah, the thought was we were going to be replacing these cables, and therefore it would not be necessary to cathodically protect those locations. But if they went through the idea that they would replace the cables and repaint the bridge, then our problem would not continue to persist.
Last question for now. What grade of steel was used to make those plates?
I think we specified all of it was.
I'm guessing that is
50
about
KSI
the clamping plates.
Yeah, I think we used 50 KSI steel for all those. There was nothing special about the clamping plates. The all-thread rods, I think, was more of a high-strength 120 KSI rod or something of this order of magnitude. But the plates, we were trying to make everything off the shelf, easily accessible. You know, there wouldn't be any special orders. What you saw there was just galvanized, or excuse me, just primed. We did not do any other painting, just primed the coat on that for, again, short-term temporary protection, and quickly could be fabricated and brought out to site and got the bridge back open.
Good. Well, thank you, Blake and Jason. We'll just wrap up the whole session right here. Thank you to all our speakers. Very good topics. I felt like 30 minutes didn't do each topic much justice, but more of an introduction. Very helpful and informative. And to those participating in this session, thank you for your time. Hopefully you'll enjoy the rest of our virtual OTEC this year. Thank you.